In this video, we're going to talk about different shapes that are inscribed or circumscribed within a circle. So the first shape we're going to look at is the square. So if it's inscribed within the circle, that means that the square is inside the circle. And you can see how they touch at 4 distinct points. Circumscribed is the opposite situation. The square is around the circle, and again there's 4 points that they're touching at. So what we're going to look at is how can you relate different lengths of the square to different lengths of the circle, and things that we'll primarily be interested in talking about, and this goes for all the shapes, is with respect to the circle, we're interested in talking about the radius and the diameter. And then for the other shapes, so the square, the triangle, and the hexagon, we're interested in the side lengths, we're interested in diagonals, we're interested in lengths across what are called flats, or lengths across angles. So we'll go through all that in the relationships. So starting with the square, we can see that the center of the circle is here, and I could draw a line like this. And what we see is this is the diameter of the circle. So the diameter of the circle is also the diagonal of the square. They are the same thing. And then you could say that half of the diagonal of the square is the radius, because we know that radius is half of the diameter. And then also, in a square, we have 90-degree angles. All 4 of the angles are 90 degrees. If this gets cut in half by the diagonal of the square, then this angle is 45. And this angle is 45 as well. And we know for a 45, 45, 90 triangle, the relationship is x, x, root 2, x. So we could also say that the diagonal right here of the square, or the diameter of the circle, they're the same thing. So let's say the diameter of the circle, it is equal to root 2 side of square. So instead of the diagonal or diameter of the circle being equal to root 2x, we say that it's equal to root 2 side of square, because the side of square is x. Okay, so those are the 2 main relationships I wanted to look at when the square is inscribed within the circle. Now let's look at this square being circumscribed about the circle. So one thing that you'll notice is if you draw your diameter of your circle here, so here's approximately the center of our circle, you'll see that this length here is the same as the side of the square. So now the diameter of our circle is equal to the side of the square. And then, of course, you can say that half of the side of the square, so this length right here, is equal to the radius of the circle. Another relationship that you can say is the diagonal of the square is equal to the square root of 2 of the diameter of the circle. So the diagonal of the square, so that's the dotted line I just drew up top, is equal to root 2 of the diameter of the circle. And again, that just comes from the 45, 45, 90 relationship. Here's a 45, here's a 45, here's a 90. So we know if this side is x, this side is x, then this length right here is the square root of 2x. So all this relationship is saying is this dotted line is equal to root 2, but instead of x, we're going to say, well, there's x, that's also the diameter of the circle. Okay, now let's take a look at triangles. We can have an inscribed triangle, so you see the triangle and the circle meet at 3 points. Or we could have a circumscribed triangle, again, they meet at 3 points. So first relationship, let's talk about the radius of the circle, and let's draw it up to one of the points of the triangle. The radius of the circle is equal to 2/3 the height of the triangle. And then the second relationship I want to look at for inscribed triangles is having to do with the side of the triangle. So this length right here. The side of the triangle and the radius of the circle, so this right here, are related by 3 over the square root of 3. So the side of the triangle is equal to this 3 over the square root of 3 times the radius of the circle. So now let's take a look at the opposite situation. The triangle is circumscribed about the circle, so it's on the outside. Let's draw the center of our circle, and let's draw the radius down. So now the radius of the circle is only 1/3 the height of the triangle. And then let's look at the same relationship. The side of the triangle, so this length right here, so side of triangle, it is equal to now 6 over root 3 of the radius of the circle. So that's the relationships for triangles and circles. The last one we're going to look at is inscribed and circumscribed hexagons. And you can see, I didn't draw this perfectly, but you can see it touches at 6 points. 1, 2, 3, 4, 5, 6. And then same thing with circumscribed. It touches at 6 points. Again, I didn't draw it perfectly, but this is the idea that it's going to touch at 6 distinct points if it's inscribed or circumscribed and it's a hexagon. So let's take a look at the relationships. First, relationships. Let's draw the diameter of the circle. So the diameter of the circle is equal to the diagonal, D-I-A-G-O-N-A-L, of the hexagon, but we have to be sort of specific here and say across corners. So you can see how we're going from an angle to an angle here. That's called across corners. But, and I'll do this in a different color, we could be going what's called across flats. So that would be this length here. So the diameter of the circle is the diagonal of the hexagon if you're going across corners. So here to here, or here to here, or here to here. But this, what's marked in green, is what's called a cross flats, and that would be a different length. And you could also have a cross flats here, or you could have a cross flats here. Another relationship that's really just within the hexagon itself, it doesn't really have anything to do with the circle, but it's useful, is the across corners, so the purple line here. That is equal to 2 sides of the hexagon. So this right here is double a side of the hexagon. And then something that you might notice is, okay, well, if this is double a side, this is also the diameter. If I take half of that, that's the radius of the circle, and half of this would be just one side. So the radius of the circle is equal to the side of the hexagon. And then finally, the last relationship I want to look at here, I'll write this in green because it has to do with the across flats, is the length across flats is equal to the square root of 3 of the side of the hexagon. Again, this really doesn't take into account the relationship between the hexagon and the circle. It's just the relationship of across flats to the side of the hexagon. However, it is a useful relationship, so I'm going to include it here. All right, let's look at our final situation. Excuse me. We have the hexagon circumscribed about the circle, so it is on the outside. We have across flats right here. That's across flats, and I could have connected here, or I could have connected here. You'll see this is the center of the circle, so across flats is also the diameter of the circle. And then if we were to go across corners, so let me switch to my purple color. So now if we were to go across corners on this hexagon, you see that that length is longer than the diameter. So across corners is equal to, and actually this is another one where it's really just a relationship within the hexagon itself, but it's useful. Across corners is 2 of the sides. And actually we have that same relationship over here because it's just related to the hexagon. It doesn't take into account how it's related to the circle. And then the final relationship I want to look at is the radius of the circle and how that relates to the side of the hexagon. So the radius of the circle is equal to the square root of 3 over 2 times the side of the hexagon.